So in this video, we are going to fully understand the concept of cross entropy piece by piece and also look at how it is used as a cost function in neural networks. We will also look at binary cross entropy and how it is derived. So this is the second video of the series. The first part was about entropy in machine learning. You should first look into that video because this video uses the concept of entropy. The link of that video is available in the description below. Okay, so in the beginning, let's assume there are 8 emojis. These emojis represent different emotions. So first one is normal, then is angry, happy, sad, sleepy, surprised, fearsome, and unwell. Let's also assume that all the emotions are equally probable, that is with a probability of 1 by 8. Now let's calculate the entropy. The formula was negative summation of p of x into log of p of x. So for the first one, which is the normal emotion emoji, we will have 1 by 8 into minus log of 1 by 8. And same for all. The entropy comes out to be 3 bits. So the best way to send this information is by using this type of coding, which is very common in computer science. As we know that the entropy is 3 bits and the sequences 000 to 111 uses only 3 bits, and hence this is the best choice. Now let's change some of the probabilities. Let's say we have 35% chance of normal, 25% chance of angry, and so on for the rest of the emojis. Now let's calculate the entropy. We again use the formula and get 2.52 bits as the answer. So our entropy has reduced from 3 bits to 2.52 bits. And if we continue using the 3-bit notation of 000 for normal, 001 for angry, and so on, which is actually requiring 3 bits, then we are not doing a very good job because our entropy is 2.52 bits, but we are using 3 bits. Well, I'll give you the reasons as to why this happened and how can we fix the problem and get codes that are better than 3 bits, but that is something for the next in-depth video. To search for it, just type datum learning cross entropy and KL divergence in depth. The important word here is in depth. So coming back, well, the reason in short is that we are using codes 000, 001 to 111, which basically and implicitly assumes a uniform distribution. For those who forgot, a uniform distribution is one where all the events have equal probabilities. Well, now you may ask that how did the codes have a probability and how they are equal? Well, it is because that their length is equal. So always remember the individual digits in the code, that is zeros and ones in any code, for example 011, they don't matter. What matters is the length of the code. Since all the codes 000 to 111 were all of length 3, they had equal probabilities. And in the initial case, all the emojis also had equal probabilities. So this is the important part here. The distribution of emojis in this case is same as the distribution of the codes, and hence we have the same number of bits. So now I think before introducing cross entropy, I should summarize what we have got till now. So we had 3 distributions. One of emojis with equal probabilities, and this is the distribution and its entropy is 3 bits. The second was the code distribution, whose probability depends on the length of the message, and this was its distribution. And it too had an entropy of 3 bits. The third distribution, which when we change the probabilities of each emojis, and its distribution was this, and the entropy was 2.52 bits. Now we are ready to understand the concept of cross entropy. Let's say we are going to encode the events or emojis of the third distribution where the probabilities are uneven with the code distribution which we used earlier. So the formula for cross entropy is h of p of q equal to minus summation of p of x times log of q of x, where p is the true, or in our case the emoji distribution, and q is the code distribution. For finding the cross entropy, we put the probabilities of the true distribution and multiply each with the code distribution used. We get 0.35 into minus log of 1 by 8 plus 0.25 into minus log of 1 by 8, and so on. At the end, we get 3 bits as an answer. Now, we also have the information of cross entropy, which is 3 bits. But if you remember, the entropy of emoji distribution in the non-equal probability case was 2.52, which means that we have a difference. The difference is 3 minus 2.52, that is 0.48, which we say KL divergence. This actually leads us to the main formula, which is cross entropy is equal to entropy plus KL divergence. Now, the problem is to find the new codes that are better to represent our second emoji distribution. Well, the way to find a better distribution is by using Huffman coding, but I'll not be getting into it in this video as it is a topic of some other video. For now, what you can do is search on YouTube Huffman coding and watch it, but make sure that the creator explains the concept in detail. So our new codes are something like this. And the important thing here to notice is that the greater the probability, the shorter the code. The probability distribution of the codes, as you can see, is something like this. Now, we should first find cross entropy where the true distribution, that is P, is distribution of emojis with uneven probabilities. The code distribution is also shown here for your reference. The way I assign probabilities is by looking at the length of the code. So for the code 11, which is for the 35% normal emoji, the probability is 1 by 2 to the power m, where m is the length of the code, which in this case is 2. So 1 by 2 to the power 2 equal to 1 by 4. For the code 0010, which is for the fearsome emoji, the probability is again 1 by 2 to the power m, where m equal to 4. So 1 by 2 to the power 4 equal to 1 by 16. So this is how the probabilities are calculated. So as you can see, there are two probability distribution. One which is the true probability distribution of the emojis, and the second one is the code distribution. Now we can put in the values and find the cross entropy. So we take the probability for the normal emoji distribution, which is 0.35, and multiply with the log of the probability of the code representing the normal emoji, which for this case is 1 by 4. Also put the negative sign. Now do this for every emoji and sum them up. The answer we get is 2.6. So our cross entropy is 2.6. If you remember, we calculated the entropy for the true distribution or the emoji distribution and we got 2.52. Now we have also seen that cross entropy is equal to entropy plus something else, which we called KL divergence. So 2.6 equal to 2.52 plus something, KL divergence. Now it turns out that we have the something which is 0.08. The derivation of KL divergence is not very important to us, but it is important that the definition of KL divergence should be kept in mind. Well, KL divergence or Kullback-Leibler divergence is just the expected number of extra bits per message needed to encode events drawn from the probability distribution P, which is the true distribution, if we are using a code for the distribution Q rather than P. Simply put, it tells us how far the true distribution is from the code distribution. Now, before I go to the part where I explain how neural networks and cross entropy go together, I just wanted to add that h of p of q, that is cross entropy for p and q, is not equal to h of q of p. This means that if we interchange our true and code distributions, our cross entropy won't remain the same. Okay, now it is time to put cross entropy and neural networks together. Let's say you are trying to classify cats, dogs, and humans using a neural network. Then, in this case, the target will be one hot encoded vector with 1 at the position of true class. Let us also assume that the first position corresponds to cat, second to dog, and third to humans. For example, if we give a picture of cat to the neural network, then our correct label should be 1, 0, and 0. Here the first label is for cats, second for dogs, and third for humans, as I told earlier. What the 1, 0, 0 for cats essentially means is the probability distribution, or in our case, the true probability distribution, which is the P in the cross entropy formula. The distribution of a cat example looks something like this. For dogs, we will have 0, 1, 0, and the true distribution will look something like this. For humans, it will be 0, 0, 1, and the true distribution will look something like this. Now, recall the neural networks. In the last layer, we have 3 output neurons giving us 3 different numbers. Since the last layer in the neural network will most probably be the softmax layer, the values at the end will add to 1 and will be non-negative, which actually means that we can use them as a proxy for the predicted or code distribution, which is the same thing. So, if a neural network predicts 0.1, 0.4 and 0.5 for a dog image, then the proxy or the code distribution will look something like this. And the real distribution, which would be, as we know, we fed the image of a dog, will be 0, 1, 0. Now we can calculate the cross entropy using the formula minus summation of p of x into log of q of x. So we will have minus 0 into log of 0.1 minus 1 into log of 0.4 and minus 0 into log of 0.5, which is 1.32 bits. Now, we will look into the most important question here, which is why is the cross entropy a valid loss function in the neural network? Well, the shorter answer is that it is having a log, and negative log is strictly decreasing and one can use it in the convex optimization. The detailed answer will be in the in-depth video. So search datum learning space entropy, cross entropy and KL divergence in depth. Last, I want to touch upon the concept of binary cross entropy, which is just the normal cross entropy written in a different way. So for the two case scenario, let's assume the two events have probability P1 of x and P2 of x. So this is our true distribution. Since P1 plus P2 equal to 1, we can say P2 equal to 1 minus P1. Now, in the binary cross entropy case, the last layer of the neural network is a sigmoid function, which will predict the probability of the input belonging to the first class whose real probability is P1. Let's say that the predicted probability was Q of x, and this is the probability of belonging to the first class. So the probability of belonging to the second class equal to 1 minus Q of x. Now let's put all the data in the table. So the true distribution values are P and 1 minus P, and the predicted probability distribution is Q and 1 minus Q. Now let's apply the cross entropy formula, and we get minus P into log of Q minus 1 minus P into log of 1 minus Q. So this is the binary cross entropy. You can see here the formula is still the same, only the second part looks a bit different. So this is the binary cross entropy. What essentially happened is the sigmoid output was taken and converted to a two event case, and the general cross entropy was applied. So that's it from my side. You can ask your questions on Instagram or in YouTube. I check Instagram more often. Please subscribe and also check out the in-depth video if you want to learn more. Thank you very much.